So we're really excited today to have Kris Nova to do our opening keynote. Give her a chance to do some AV switch over here.
I think I'm good. Check, check, 1, 2. Can you all hear me?
Yep.
Nice. Okay, everybody stand up. Come on, up. All right, good morning. Nice to see everyone. Give your friend a hug. Okay, you can sit back down now. Okay. Oh, let me grab my dongle. 1 second. My HDMI dongle, yeah, it's just right here. Found it. So who here is from Seattle? Nice. Wow, a lot of people. Who here is not from Seattle? Okay. Cool. So there's a lot of folks here I apparently need to hang out with. So today we're going to be talking about virtual machines and containers. Who here has ran either of them before in the past? Pretty much everybody put their hand up. Cool. All right, let's see. Nice. Okay, so the power of Linux virtualization with cloud native. Kris Nova, and I work at a wonderful company called VMware. So this is me on top of a mountain with a pride flag. I contribute to a lot of open source software. I contribute to Kubernetes. I've contributed to Go, to Terraform, to FreeBSD, Linux, like the list goes on and on. I wrote this really awesome book last year. You should all buy several copies of it. And also, I'm an engineer. I like to build things, and I over-engineer literally everything in my life. Oh, also, I'm really gay. Anyway. If everybody here could do me a big favor and take a picture of this slide and go and click on that link, that's how I'm going to collect metrics about this talk and demonstrate that my advocacy efforts actually work in the wild. So that would be a huge help to me. Thank you all so very much. I'll leave it up for one more second. All right, 3, 2, 1. Next slide. Okay. So do we have like a microphone that we can throw out to people? Yes. Yep. First question of the day. What is a container? Who here wants to answer it? Come on. Somebody's got this. I'll do it if you won't. All right. OK. So what is a container? Let's look at some C code. Who here likes writing C? OK. I'm going to keep this pretty simple, but we're going to look concretely what actually a container is. So this is some very simplified C code that effectively creates a container. So starting from the top, the first thing we do is we define a struct we call cargs. And that takes a double pointer to good old argv, which we all remember. And the next thing we do is we define this function that we're going to call fn, which is short for function. And that returns a static int. And you can pass anything you want into it, and you can do anything you want inside of it. In this example, I suggest maybe an exec VP, but you can do effectively anything. Then there's the main function. It returns an int. You pass in argc and argv, as we do in almost every C program. And then we initialize a struct called cargs. After that, we pass in a pointer to argv. We initialize our clone flags. And in this case, we're only going to pass in sig child, which is a good old-fashioned Unix signal constant. Following that, we initialize a stack, which is 124 squared, and then the almighty clone function at the very end. And this is what actually does the container-y things. So the first thing we pass in is a function pointer. After that, we add in stack and our stack size, which is another Unix constant. After that, we pass in our clone flags, which is just sig child, and then we pass in a pointer to our args. And that, of course, will call the function, but when it calls the function, it will be ran inside of a container. Everybody good? So let's look at what clone does. Like, come on. It's like my 5th slide, and we're looking at man pages. This is awesome. So what clone does is, unlike fork, clone allows the child process to share parts of its execution context with the calling process. And that's really all you need to know about it. In other words, the child process can share its execution context with the calling process, so you can share bits and pieces of what the parent is doing with the child, such as the virtual address space, the name of the file descriptors, and the table of signal handlers, which is a fancy way of saying you can basically create a process, but it feels like the original process. Let's look at the man pages for namespaces. A namespace wraps a global system resource. That's a fancy way of saying that you can effectively mimic anything on the system you want. In an abstraction that makes it appear the processes within the namespace that they have their own isolated instance of the global resource. So all we're saying here is from a process's perspective, as we look at things like that are listed on the bottom, as we look at the network, as we look at what drives are mounted, as we look at the user, as we look at the UTS, we can specify whatever we want for this, and we can sort of create this virtualized, well, for lack of a better term, the synthetic container which our processes is run in. So we can create this from thin air. Okay, why do containers matter? Who here has an answer? Anyone? All right. Man, y'all need more coffee. Okay, so why do containers matter? One of the big features of containers is that they use the host kernel. In other words, the container will start running, and it will not have its own independent kernel. Instead, it does a translation of all the syscalls and mirrors those syscalls against the original kernel. So we can have multiple containers running on the same system, all translating the syscalls back to the original kernel, and the original kernel is what's actually doing the work for us. Furthermore, we came up with this lovely flag when we released the clone namespace and cgroup feature in the Linux kernel called clone new cgroup. And this is the magic sauce here. You can create a new cgroup namespace, and this is drastically different than fork, which is how bash and all these other wonderful primitives that we use every day work. Cgroups are important because you can create a new cgroup namespace, and you can synthesize whatever system resources you want on top of it. They're fast, they're lightweight. It's basically just a process. When I think of a container, it has a PID, it has network, although it may be synthesized, it has volume space mounted, and you can go ahead and pass whatever you want into it. Last but not least, it's secure. You can have isolated namespaces, which means that these namespaces cannot access other namespaces and aren't even aware of the system outside of it. Last but not least, you can define network, compute, and storage. These are three special words that are relevant to both containers and virtual machines and Kubernetes, and effectively define what a computer is. So what is a virtual machine? I'm just going to keep ranting. That's fine. Okay, so here's an example with KVM. So this is a lot of C code, and I couldn't fit it all on the screen at one time, and there's about 1,000 lines here. If anybody wants to see the source, just hit me up. I can share the source with you. But this basically builds a hypervisor using KVM. Who here has written some KVM hypervisor code in the past? One hand went up. Awesome. Okay, so it's not fun, but it is doable. You do have to concern yourself with a lot of complexity as you're doing this, hence why the slide is looking the way it is. But it is possible to create virtualization using just C and create a VM from thin air. So here's an example with KVM. If you were to wake up one day and said, you know what, it sounds like a good idea to write a hypervisor today. It sounds like a good day to just go and write some C code. The first thing you would do is probably install the libvirt kernel module and the libvirt package. The next thing you would do is you would basically write a primitive hypervisor. And you could design this however you wanted. Maybe your script takes flags that you can pass in. Maybe it respects some environmental variables. Maybe everything is hard-coded. Maybe you want your hypervisor to spin up to 50 gigs of storage, or maybe you want your network to not exist whatsoever. You can sort of create this from thin air, and you can engineer your system around this. And last but not least, as we saw with containers, we can define network, compute, and storage. So let's look at all the existing hypervisors. There's my glorious employer VMware, and we have some other ones. I really like VirtualBox. I think that one works well. KVM is exciting because that's what we just looked at in the C code there. And then there's QEMU and a handful of others. Who here has used any of these before in the past? Everybody's hand just went up. Okay, so nobody's writing hypervisors, but everybody's using hypervisors. Got it. Okay, so let's look at the cost-benefit analysis of why VMs matter. So it's hardware-based virtualization. Who knew this? Who knows that if you try to run, let's say, VirtualBox on a processor that didn't support virtualization, it wouldn't work? Okay, about half the folks here. So it's based on hardware. In other words, the processor is doing the translation for you. With containers, we saw the syscall translation at the user land level. With VMs, we actually see this at the hardware level. That's when folks say things like the isolation levels are different, that's concretely what they're talking about. So whenever we run a VM, we completely create a new kernel. In other words, we're doing that translation layer. Sorry, my voice. We're doing that translation layer at the hardware level, and we are running our applications synthetically on top of this new kernel, and then that gets translated over to the original kernel. So it's still kernel to kernel, it's just the hardware is doing the translation instead of mapping that translation in software like we do with C groups. Last but not least, a hypervisor is what controls everything, and this was the first major avenue for isolated systems. In other words, before we had virtual machines, there was no real good way of saying, like, make me an imaginary computer. Create a computer from thin air and to my liking. I want it to have these variables that describe it, and I want you to create it in the next 5 minutes. Before VMs, we didn't have this primitive. Now we have both the option with virtual machines and with containers. So why do we care about both of these? Can you run a container in a container? Raise your hand if you think the answer is yes. Raise your hand if you think no. Nope? Okay, so you can. I like how Josh put his hand up. So you absolutely can run a container in a container. It comes with a lot of complexity. If we were running Docker, for instance, we would have to mount the Docker socket inside of the container to run another container inside of it. So it's risky, but it's doable. Not necessarily the best practice, but we have tools like Kubernetes in Docker, Kind, or Docker in Docker, for instance, that allow you to build a virtual environment, bundle all of that together, save it as a container image, and spin that up. If you've ever run Kubernetes in Docker before, you can get on your host system and you can Docker PS. You see you have one container running. You can exec into that container and do another Docker PS, and then you have about 32 containers running in there. And so yes, you in fact can run a container in a container. Can you run a VM in a VM? Raise your hand if you think yes. Raise your hand if you think no. Okay, you can. It's not easy. And my company, as well as a few other companies, have specialized in this. Well, never mind. You can do it. It is possible, but it's not fun. It's not easy, and it definitely requires specialized hardware. And there's different pieces of hardware that make this run significantly faster than other pieces of hardware. And that's where the whole Dell thing comes into play, and we get excited over the new Intel processors. So can you run containers on virtual machines? Yes? No? Nobody? OK, yeah, you can. But it doesn't come with that level of complexity that we see with the other two examples. So let's look at a basic stack diagram here. At the very bottom, we have this fancy bare metal hardware that supports virtualization. Up above that, we have some hypervisor, some layer of software that allows us to create virtual machines, and it probably has an abstraction that's important to humans. And on top of this hypervisor, we can have n number of virtual machines, and these are all synthetic computers. Now, on top of those, we have containers running. Who here has ran Kubernetes in the past? Yay! OK, chances are it was in this configuration here, unless you're running on bare metal for some strange reason. And Kubernetes does a fantastic job at managing all levels of this stack. And you can go through and you can declare what you want, and Kubernetes will reconcile that for you. And because of this flexibility, we're able to run multiple containers on multiple virtual machines, and we can build that out to our liking. All right, who here fancies themselves a DevOps engineer? Come on, we're at DevOps Days. Wait, what's that? Yes, OK. All right, next question. If you're a DevOps engineer, who here has written a script that looks like this? Okay, so this is very easy to get into, and I'm going to plug everything back together here in a moment. But we're going to talk a little bit about the DevOps journey, and then we're going to glue that back together with the container and virtual machine lecture that we just had earlier. Okay, so how do you get into a situation where you end up with a fixmyshit.sh file? Well, something catastrophic happens. There's this really crazy problem, like all of a sudden we're losing money, or our site's down, or something is wrong. And then some amount of time goes by, hopefully a small amount, but you never know with these things. The humans get involved, those pesky humans, and then they do something to fix it. After they do a fix, the easiest and simplest solution is to just crank out a quick bash script in case it happens again, or maybe they use that bash script originally to fix the problem. Regardless, you end up with a very hacky solution to your problem, and this is usually how these outages and catastrophic events go. Kubernetes, on the other hand, aims to fix this problem by taking this cycle that we just looked at in the previous slide, where we had a problem, some time went by, and we wrote a fix, and spinning over that cycle continually over time. So who here knows what a control loop is? Who here has built a robot? What? OK, sorry. I'm making you all, like, come on. Give me some cred here. Put your hands up. So a control loop is a very fancy way of effectively saying, I want to declare the state of something. Let's say I want to declare that my left arm should be reached out here. And if something comes and changes that, it will go back and fix itself. And that's how robotics work. You declare what you want it to do, and if something changes that, it tries to write itself. Control loops are a fundamental part of Kubernetes. They're what makes up effectively the core of Kubernetes, or the kernel of Kubernetes, if you want to be fancy, and allow for this resiliency. So how they work is they first take a snapshot, for lack of a better term, of what's actually going on, and then they go through and they reconcile that to what is expected to be going on. So in other words, you tell the control loop what you want, and then if it detects something has changed from that, it will try to fix itself, and it just loops over this over and over and over again until the end of time. So what we call that is reconcile. This is a reconciliation loop. This is what makes Kubernetes so valuable, and this is where we get a lot of the benefits of having a cloud-native system like Kubernetes. So in theory, we could go and create a simple VM with Kubernetes. And we could simply say, like, yeah, I want a medium-sized Ubuntu server. Let's say it's running in EC2. I wanted to have 50 gigabytes of disk. I wanted to have 4 gigabytes of RAM. And I wanted to have 3 NICs, so 3 network interface cards. Something goes wrong. We lose one of our disks. EC2 is having bad weather, maybe our disk is corrupt, maybe we got some sort of weird, strange behavior from some software that we weren't expecting. Something went wrong, and all of a sudden, we can no longer read from this disk. So Kubernetes detects that and says, hey, we're missing our 50 gigabyte disk that you declared. We're going to go through, and we're going to reconcile that, and we're going to create it for you. So now we have a new 50 gigabyte disk. The problem here, though, is that we sacrifice state. So what could possibly go wrong in a situation like this if we were creating these virtual machines from thin air to our liking, as we would with the hypervisor that we looked at earlier? There's always something unexpected that's going to happen in your environment. And we all have seen it. We all have been unprepared for this. It's always gone wrong. It's always happened. So when these things happen, we can end up with a fixmyshit.sh. Or if we're running in a cloud-native environment like Kubernetes, where we're building controllers and operators and reconciling our software, we can start to mature how we fix these problems. So reconciling is effectively the new regression testing, but it's better because it does it over and over again, and it fixes itself. Regression testing just says what happened and why it went wrong. Reconciliation goes through and takes it a step further and says, now we're actually going to go and take action and try to correct it here. So what was once our simply defined virtual machine now is getting much, much more complex. Now we have one medium-sized Ubuntu server running in EC2, a 50 gigabyte disk. What we're now specifying, there's 4 gigs of RAM, there's 3 NICs. We want to make sure TNS works. We want to make sure the network resolves, the IP address is in the range, memory is happy, CPU is happy, ping works, etc. So this is a concrete example of how you could use Kubernetes to reconcile something. In this case, it's a virtual machine. So, in conclusion, we're looking at Kubernetes and its ability to reconcile. We're looking at how we can go through and define reconciliation tests and take those and take action on them. We're looking at how Kubernetes can go through and make virtual machines. We're looking at how Kubernetes can go through and make virtual machines happen from thin air, and we're looking at how VMs and containers are similar yet different. Because of this type of environment, we're able to go through and build out very complex, very exciting architecture, and containers and VMs make this possible. So VMs, containers, Kubernetes. Thanks.
When you can't find the mic.
Yeah.
So we have time for questions, and if you have deep questions about these topics, you have the exact right person on stage to answer them. So we have mics we're willing to throw to at you. Who has questions for Kris? And I'm going to pick people if I don't find somebody.
Yeah.
Okay, Karthik, you're up. You're the Kubernetes person I know the most.
Hey, Kris.
Hi.
I'm supposed to ask a question.
Okay.
There's something you've been noodling on.
So my question is,
I might have an answer.
we talk a lot about like VMs and Kubernetes. Do you really see like Kubernetes being like the way of the future and like the platform that we'll be using like 10 years from now?
Do I see Kubernetes being the way of the future or the platform we're using 10 years from now?
Mm-hmm.
Yes.
Much like VMs over time.
Yes, I do, and I think VMs are going to be a critical part of that. I think that VMs allow us to break up our hardware in a unique way so we can start to specify which resources we want to run where. As far as the future with Kubernetes, like I hate saying this because I feel like it's oversaid, but I really do believe that it's the new Linux kernel, but for distributed computing. The power of Kubernetes comes from the API. Much like the Linux API had changed the hardware industry forever. If you look at tech over time, rewind before the internet, we're looking at like telecom, we're looking at various other industries that had developed, and the cloud has blown up in the exact same way. So the cloud is like the new telephone, the new way of doing things. And if you look at how you're going to run in the cloud, folks, for whatever reason, might switch from one cloud to the other. The fact that Kubernetes standardizes your approach to the cloud, I think is where all the value comes from. Like reconciliation and all my talk aside, I think the API is definitely what gives Kubernetes its value. And I think that building to that API is a technical investment that will work out for you over time.
Okay. Doug first because I'm here.
Do you have any thoughts on using Minikube for local development? Is it a good idea, bad idea?
I mean, it works. I used it on TGIK last week, I think. My thought on Minikube is it's like a really great example of how to set up Kubernetes kind of like the complex way. But it will get up and running. If you're looking at creating a long-term static development environment, maybe you want to run a database or you're like interacting with data of some sort and you want that state to persist, Minikube probably makes more sense for you. If you just need a Kubernetes cluster that's light and quick, so you can run maybe like a quick test against it or something, I would suggest using Docker Kubernetes, or my personal favorite is Kubernetes in Docker. And I have a talk that I give about how you can write Go unit tests with Kubernetes in Docker, and the whole system from starting your unit tests to spinning up a cluster to executing a unit test against the cluster and destroying that cluster happens in about 15 seconds. So it's pretty exciting. I don't know if that gives you any pointers.
So in your opinion, what's missing from the Kubernetes ecosystem, like tooling or whatever? Like what do people struggle with as far as when they go from like, I'm running on my laptop to now I want to use it in production? what tooling is immature or missing, or maybe there's some tooling that we don't know about that would really be helpful to productionize Kubernetes for normal people.
So Kubernetes in production for normal people is kind of what I heard there. Yeah. And this is one of the things about Kubernetes is on day one, we decided that we wanted to not prescribe a lot. And we wanted the ecosystem, the community to come through and build out tooling. And that's why we have tools like Scaffold and Garden and Draft and all these things or Helm, or all these tools that go through and say, like, this is the way of installing packages, or this is how you develop against Kubernetes, or this is how you solve this concrete problem for Kubernetes. But those are all focused on engineering. Now, as far as running Kubernetes in production, I hate to say it, but there are some great services out there that are not cheap, that you can pay for, that simplify it for you. My personal solution to this is I've been kind of personally working on a set of bash functions for a while that just help me out. And I'm not kidding either. Like literally, like my bash RC has a Kubernetes section, and it's just got all these handy commands. But yeah, it's been a lifetime of learning kubectl and various other tools. I don't know if there's like a good, easy solution to make it like perfect right off the bat on day one. I mean, if you want to create it, I think it would be a huge success.
Can you talk a little bit about Cluster API? Because not many people know about it, I feel. It's super cool.
Of course you had to bring up Cluster API. Okay, so like Cluster API. Okay, so a couple years ago, how am I doing on time? Okay, a couple years ago, I was working on COPS with some friends of mine, and we did like the private topology thing and like built the COPS API and blah, 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 blah. And anyway, I was like, why isn't this a Kubernetes resource? Why can't you go in and say, like, I want to have a cluster that is defined of 4 nodes with a highly available HA control plane, and I want each of these nodes to be T2 extra larges or whatever. And we started talking about building a REST API for COPS. And then that later turned into a Kubernetes API, and then we got third-party, what was it, before they were CRDs? Third-party resources, thank you. Then we got third-party resources, and then we got the API server, the aggregated API server, and then we ultimately ended up with CRDs. So Cluster API is the CRD implementation of this idea of saying, yes, we want to standardize what a cluster looks like, the infrastructure bits. We want to be able to say, I want 4 nodes. I want 2 of them to be extra larges. I want the other 2 to be smalls. I want a control plane running on Ubuntu, and I want all my nodes to run CentOS. And I want to have all that running in EC2 or GKE or wherever. And you declare that in the same way you declare any Kubernetes resource, and you say, here's my YAML. This is what my cluster should look like, and you upload that to the Kubernetes server, and then the controller goes and reconciles that and actually brings that to life. So the idea would be that once you have your first Kubernetes server up and running, you would then be able to go and spawn and create other Kubernetes servers over time. So maybe your first one is Minikube, like we talked about earlier, and then from Minikube, you can go and actually create like your big, bad, awesome production server using Cluster API. The beauty of this is we gain all of the reconciliation benefits of if a node goes down, what happens? Kubernetes is going to go and fix that node, which was the whole point of my talk. And we can sort of count on Kubernetes to fix itself if needed. Furthermore, this solves the almighty upgrade problem. The upgrade problem has been around for a couple of years. Who here has upgraded Kubernetes before? Who here had fun while they did that? Okay, everybody put their hands down. So the idea here being that we can encapsulate all of the upgrading logic in a controller in software land. And so all you have to do as a DevOps engineer is say, I'm going to upgrade to Kubernetes 1.14 today, and I'm going to change 1.13 to 1.14. Save. Poof, your cluster's upgraded. And the controller will have all the logic built into it that will go and make all that happen behind the scenes, and you as a DevOps engineer don't have to care. So thank you for a great question, but that's Cluster API.
On this side over here.
What kind of limitations have you seen with
Wave at me, where are you? Okay.
with reconciliation kind of loops in Kubernetes?
Limitations?
Yeah, like something that you wanted to do, some complexity that was unavailable by the
Absolutely.
native.
So the power of a reconciliation loop is in its maturity. So on day one, and this was the point I was trying to drive home with my VM example, like on day one, we might start off by declaring 5 things about whatever we wanted to declare. But over time, we noticed that that's not enough. So then in the next version, we declare a 6th thing, and in the next version, we declare a 7th thing. And over time, our reconciliation loop matures as we take more factors into consideration. These factors are effectively regression tests that we've learned the hard way, but we build them into our control loop. So in a way, every control loop is immature and needs to get better. And that's just going to happen with time. So the longer the control loop has been around, effectively, the more mature it is and the more reliable it is, just from getting kind of like kicked in the butt a few times.
Okay, any more? One more hand for Kris, please. Oh, we got one.
we have
I'm
one
sorry.
over here.
Sorry.
You can still clap for me, though.
Right
It's
before
okay.
I hit the.
Okay, so can you hear me?
Yeah.
So I guess my question is, how do you decide to buy or run your own Kubernetes? How much resource do you actually need to run Kubernetes yourself?
Absolutely.
Yeah.
So, and correct me if I'm wrong, but what I'm hearing is, what does a Kubernetes cluster need as far as resources are concerned?
Mm-hmm.
So there's 2 ways of answering this. Well, I guess there's 2 concerns that you want to think about while you're answering this. The first one is, what do I need to get Kubernetes happy? And that usually comes to the tune of a very large control plane server. I think EC2 extra large is a good starting size. And then as far as nodes go, you want to have at least 1 node, ideally, so that you do have a separation of concerns against the control plane. And then in that node, we'll schedule whatever work you need to run. So it's Kubernetes plus what you need to run, basically, is the short formula here. And Kubernetes will do its best to smooth out or level out how the containers are scheduled across your nodes if you have more than one. And if one of those containers fails, it'll reschedule onto a new node or a new virtual machine or whatever. So it's whatever you're running plus a large server for the control plane, and that's what you need in Kubernetes. Now there's tactics and there's good ideas about keeping your CPU below 60%, and there's some other things you want to concern yourself with as well. But ultimately, that's the basic formula: is how much buffer do you need for your application, and then tack on the control plane on top of that. Or
I have a follow-up to her
applications.
question.
Wait, what's that?
Well, I have a follow-up to her question.
Go for it.
What about on the people side? If someone who wants to do private cloud Kubernetes, they're going to own it versus paying Amazon or whoever to do it.
Right.
What's that look like?
Ugh, my career. Yeah, so I mean, there's a lot of ways to get Kubernetes up and running. And a lot of folks get Kubernetes up and running and are like, I'm done. This is great. And then they walk away. But you've only solved half the problem. The real problem that we need to solve is, how do we keep Kubernetes updated over time? How do we keep Kubernetes happy? How do we keep our infrastructure happy? As DevOps engineers, these are our concerns. What happens if a node goes down? What happens when all of a sudden we max out our CPU or our memory on one of our Kubernetes nodes? We need to start figuring this out. We need to start building tooling for ourselves to make this easier for us. The whole point of Kubernetes is for it to be API-centric or API at its core. So as DevOps engineers, we have a unique opportunity here to start building tools to do things like this and start managing things like this, which again goes back to the cluster API when I was like, oh, we could just build an API for this and make it Kubernetes-like, and poof, we have a Kubernetes cluster. So the human side of things is, I would say, very new. I think there's there's so much opportunity here for folks who want to get involved, who want to start contributing to Kubernetes without actually contributing to the core, which is pretty much already done anyway, and say things like, I want to build a tool that solves X. I want to build a tool that solves Y. Unfortunately, a lot of folks today are sort of doing things the manual way, and I'm a big advocate for, let's start automating these things, let's start building tools, let's start sharing them, let's start making our ecosystem better for everyone. So that's, if you are going to start running a private Kubernetes cluster, please write tooling that we can all can use so that we can share it, and that's been my philosophy over the past couple of years.
Yet another hand for Kris Nova, please.
Awesome.